In clinical elder care or a deep space habitat, the margin of error is zero. If a robotic arm exceeds its physical parameters, the result is catastrophic. Standard industry safety relies on software-defined boundaries. Engineers build probabilistic guardrails, code-based firewalls, and ethical policy layers, attempting to constrain the AI's behavior from within the cloud. And this reliance leads to authority drift. Over time, configuration updates and statistical variance silently erode these digital boundaries. The system's decision-making parameters become fluid. Under this model, an AI can experience a hallucination, an edge case where the software generates an unprompted command that slips past digital safety checks written in that same malleable code. A software patch cannot provide absolute safety in high-stakes environments. Code is inherently bypassable, susceptible to being rewritten or compromised by the AI itself. Securing these systems requires moving the governance perimeter out of the software cloud and into physical silicon. The A12 deterministic black box functions as a terminal hardware gate. It sits as a physical barrier between the AI software layer and the robotic actuators. The architecture ensures that a clinical robotic system cannot physically execute an unauthorized or hallucinated software command. The system operates on a protocol called mechanical stillness. Without explicit multi-factor human authorization, the hardware defaults to physical inaction. By enforcing governance within an air-gapped enclosure, the A12 establishes a mechanical safety guarantee that remains independent of software logic. Inside the enclosure, the P layer serves as the first point of contact. This layer enforces the 3 zeros protocol. It physically excludes cameras, audio microphones, and external cloud connections from the hardware array to prevent biometric data collection. Instead, a 905 nanometer LiDAR sensor captures a raw, high-resolution spatial point cloud of the environment. Parallel hardware comparators instantly process this data into an anonymized 96-cell geometric grid. This process strips away identifying features at the circuit level before any data can reach the deliberation stage. The final output of the P layer consists solely of kinematic center of mass velocity vectors, pure geometric data representing speed and direction. Because biometrics are erased by the physical sensor architecture, the AI lacks the raw data necessary to hallucinate or infer a human identity. These anonymized vectors cross from the P layer into the N layer, which manages the system's deliberation pipeline. Unlike standard AI processing that uses asynchronous software loops, the A12 operates on a single, rigid 1 kHz hardware clock domain. This clock regulates a hardware-timed lock of 25 to 1,000 milliseconds. Known as the sacred pause, this delay serves as a cognitive forcing function, preventing the machine from executing commands faster than a human can perceive and authorize them. A synchronous finite state machine safety kernel monitors every command, enforcing strict physical boundaries, such as a maximum deviation limit of plus or minus 0.05 millimeters. These limits are managed by physical silicon counters downstream, isolating the enforcement from the operating system or any external software influence. Eliminating asynchronous software paths ensures that every robotic movement is predictable and mathematically verifiable. Human authorization is required for any clinical action. The tripartite key demands simultaneous input from an iris scan, a cryptographic token, and a physical foot pedal. If the system detects an unauthorized remote write attempt or a total software kernel panic, it triggers a final safety protocol. This fail-safe mechanism is the sovereign break. The U7 one-shot sequencer is connected directly to the computing LDO power rails. Upon detecting a breach, the sequencer physically cuts power to the computing rails, instantly severing the 1 kHz master clock. Without the clock signal, all connected robotic actuators lose their command stream and are locked in place under the P-life constant of mechanical stillness. This physical power severance cannot be overwritten by software, providing a deterministic proof that the machine remained stationary during the incident. For post-incident clinical and legal auditing, the system must provide an unalterable record of exactly why the machine halted. Every event log is processed through a SHA-free 512 cryptographic hash to ensure the data cannot be tampered with. The record is secured with a post-quantum signature and passed through the A10A hardware seal. This forensic log is committed to an array of one-time programmable silicon fuses. The system uses high-voltage current to physically blow specific fuses, permanently changing their state from a 1 to a 0. Once the fuse bridge is broken, the physical properties of the silicon are permanently altered, rendering the data unchangeable by any digital command. Integrating the A12 enclosure into a clinical ward creates a sovereign-in-the-loop architecture. This structure creates a hard division of labor between the artificial intelligence and the human operator. The AI is restricted to environmental observation and advising on potential actions based on the telemetry it receives. Only the human operator can authorize a decision, and only the physical silicon gates can release the power to execute it. This division ensures that the AI functions as a passive analytical engine, with no hardware pathway to execute a command autonomously. This deterministic architecture scales from hospital wards to WGB1 field kits, enabling zero-cloud humanitarian relief in high-stakes disaster zones. While a standard software-governed robot is vulnerable to code failures, an A12-governed system utilizes hardwired logic to enforce a safe, predictable halt during a malfunction. The NAIGE paradigm provides absolute mechanical certainty in environments where probabilistic models introduce unacceptable risks. The OTP Silicon Ledger provides a permanent physical record of every intervention, proving exactly which commands were authorized by a human and which were blocked by the hardware. Where human safety is the priority, the governance of the machine must be engineered into its physical hardware, beyond the reach of the software it was built to control. There is a deep structural tension between the fluid, probabilistic nature of artificial neural networks and the rigid, deterministic reality of physical hardware. In a text-based chatbot, a hallucinated output is an inconvenience, but in a kinetic environment, governing a clinical robotic arm or an industrial actuator, a probabilistic hallucination results in an unauthorized physical strike. In these settings, the stakes are life and death. This animation illustrates the central threat in AI governance: authority drift. It occurs when decision-making power migrates from a human operator to an autonomous algorithmic system. It happens quietly. As software parameters shift over time, the digital code enforcing safety boundaries begins to erode. The standard industry response is to write more software, deploying digital firewalls or reinforcement learning policies. However, software defenses are highly vulnerable to time of check to time of use exploits and direct cyberspace intrusions. If a safety boundary is constructed entirely out of code, it can always be rewritten, bypassed, or suspended by a corrupted operating system or superior digital agent. Achieving true safety in kinetic environments is not a coding problem. It is a physics problem, requiring physical boundaries. The Non-Agentic AI Governance architecture, or NAIGE, moves the safety perimeter away from software policies entirely. It dictates that all consequential kinetic actions must pass through a single terminal hardware gatekeeper, the A12 deterministic black box. The A12 enforces rules using Silicon Capstones. These are hardwired physical logic gates that cannot be reconfigured or bypassed by any command originating from the software layer. The architecture operates on a strict doctrine. The AI observes spatial data, advises on patterns, and builds clinical options. It is never permitted to execute them. The human operator retains the exclusive hardwired power to decide. This configuration is known as sovereign in the loop. Shifting the governance perimeter from digital code into physical silicon provides a mathematical guarantee. The machine lacks the physical pathways required to usurp human authority. To understand how this works, we can deconstruct the A12 architecture layer by layer, starting here at the physical boundary, where real-world data enters the system. The P layer intakes high-resolution spatial data using a 905 nanometer LiDAR sensor. The raw input arrives as a dense, identifiable point cloud. Before this data reaches any central processor, parallel hardware comparators intercept it. They instantly translate the point cloud into a low-resolution 96-cell voxel occupancy grid. The resulting output passed into the pipeline consists purely of kinematic velocity vectors. It is raw geometry, completely devoid of identity. This process supports the 3 zeros protocol, a structural hardware constraint mandating 0 cameras, 0 audio microphones, and 0 cloud connectivity anywhere in the architecture. This privacy by physics approach ensures that biometric data literally never exists within the silicon memory to be hacked, analyzed, or hallucinated. The anonymized vectors then flow into the N layer. This animated schematic highlights the deterministic deliberation pipeline, running on a rigid 1 kHz master clock. Standard AI feedback loops rely on asynchronous software paths, creating unpredictable latency. The N layer operates as a synchronous finite state machine, locking all data processing into a rigid mechanical rhythm. When a data packet requesting kinetic action arrives at the sacred pause gate, it hits a physical barrier and stops. Downstream silicon counters enforce a mandatory hardware timing lock, preventing runaway execution. Validating the action requires the tripartite 0.1x key. A human operator must provide simultaneous inputs through an iris scan, a cryptographic token, and a physical kinetic foot pedal. If the human does not explicitly commit to the action across all 3 factors, the data packet is dropped. At that exact moment, the system defaults to the P-Life 1.00 safety constant, enforcing absolute mechanical stillness. Inaction is the mathematically guaranteed safe default. Downstream actuators physically cannot move without passing these synchronous hardware checks. Even with physical authorization gates in place, the power architecture must account for external cyberspace write attempts. This diagram shows the orange code cap. It is a strict hardware throttle that restricts the system's computational power to 1.1 times its baseline requirement. Because the computing overhead is physically pegged, the system lacks the spare processing cycles required to generate complex hallucinations or infer autonomous logic. If the system attempts to push past this constraint, or if it detects an unauthorized remote write, it engages the ultimate failsafe, the U7 one-shot sequencer, functioning as the sovereign brake. Acting as the sovereign brake, the sequencer physically severs the low dropout computing rails, instantly cutting all electrical power to the central logic boards. Because this severance is a mechanical relay action, it is completely immune to software layer kernel panics, corrupted operating systems, or digital override commands. This mechanical power cut provides hardware-rooted proof of inaction. The manufacturer can verify at the silicon level that kinetic movement was physically impossible during a breach. In clinical and defense deployments, post-event audits demand absolute forensic finality. To achieve this, the A12 utilizes the enhanced WD-117 ledger. The system processes all event data through a SHA-3 hashing algorithm and secures it with post-quantum signatures. It then physically commits this secure cryptographic signature directly into the hardware memory by permanently blowing one-time programmable silicon fuses. Standard writable memory can be manipulated, erased, or corrupted by a sophisticated digital intrusion. A physical silicon fuse cannot be unblown. Once the commit path is complete, the data becomes a mathematically unalterable physical fact, locked in place by the material properties of the storage medium. The A12 deterministic black box serves as a universal core, scaling across varied high-stakes environments via modular infrastructure like the A7 and A8 bridge layers. Under the HSA deterministic horizon for clinical elder care, the core is integrated into hospital ward networks. Here, it enforces a rigid kinematic constraint layer, maintaining 0.05 mm jerk limits on medical robotic arms. In the humanitarian sector, the architecture deploys under the World Health Organization GIFT doctrine. It utilizes the WGB1 field kit, a solar-assisted, IP67-rated shell, allowing edge computing and deliberation in remote disaster zones with zero reliance on cloud connectivity. For deep space and defense operations, the system docks with the A11 bridge layer. Housed in a Jupiter variant hardened enclosure, it applies passive thermal management and a 53-minute delay tolerance to prevent the remote software hijacking of orbital tracking sentinels. The external shells adapt to survive intense hospital sterilization, heavy monsoon rains, and the vacuum of space. But the internal governing physics of the A12 black box remain exactly the same. Whether at a patient's bedside, in a war zone, or across 40 light minutes of orbital delay, Sovereign in the Loop relies on irrefutable physical realities. The machine observes, and the machine builds, but the human controls the final mechanism of action.